Hey, anybody hear me? Or oops, great. Got 4 people. Can you guys hear me? Oh, okay, that's good. Great. Okay, great. So let's start. So there are not too many of you here, but let's start with some exercises. Please let me know if you can't see the board. Okay. First, an exercise on cyclic groups. Give a group and let X be a G with order N. Show that the subgroup generated by X to the M is equal to the subgroup generated by GCD. Is the board clear? You, anyone? The board. Can you guys read? Yeah, okay, very good. Okay. Great. Let's prove this. Okay, just I need another confirmation that you can read what's on the board. Please. Just a yes or no. 2 more students or 1 more. Okay. Yeah, okay, great. Awesome. Okay, so let's prove this. Now the idea here is not to go by brute force. The idea is to use the theorem that we learned about cyclic groups. So X has order n. So the group, so the subgroup generated by X is a cyclic group with n elements, a cyclic group of order n. Hence, I know for every divisor of n, every positive divisor g of n, there exists a unique subgroup of X, the elements. Okay. Now let's look at the order of X to the m. X to the m has order. The order of X has order n over GCD mn. Right? By the formula we know about the order. So the n here is really, if you want to be a bit more precise, this n here, this is the order of X over GCD order of X m, which is n over GCD. Hence the subgroup generated by X to the m as n over GCD n. Now let's look at the order of X, GCD, and M. The order of this one has order N over GCD N and GCD M. Now, if you look at this, you know that the GCD Mn divides N. Therefore, the GCD of N and GCD Mn, GCD Mn divides N with GCD N and GCD Mn is equal to GCD Mn. So really, this has order I'll just erase this. This is like this. The GCD Mn divides N, so the GCD of these two is this one. Okay? Well, let's write since. Hence, the subgroup generated by X GCD Mn has N over GCD Mn elements. Now I know that the subgroup generated by X is a cyclic group. And hence for every divisor D, I have a unique subgroup with D elements. This is a subgroup with N over GCD Mn elements. It's a subgroup of the cyclic group X. And this is a subgroup of the cyclic group X with N over GCD Mn elements. By the uniqueness part, these two subgroups must be unique. Okay. Any question? Good. This is a cool exercise on cyclic groups. We could do another one, maybe. Well, any questions? Great. Okay. Okay. That's another exercise on cyclic group. Exercise 2. Show that any subgroup of Z is of the form NZ sum M N the answer. So really all the subgroups of Z are just the multiples of some element, basically. Let's prove it. So let H be a subgroup of Z. Or Z here is taken with respect to addition. If h is 0, if h is just a 0 subgroup, the identity take and h is equal to 0. Take all the integers and multiply them by 0. What do you get? You get 0. Now suppose h is different than 0. Then there exists m of z and m different than 0 such that m belongs to h. So if h is non-zero, then I can find an element m and z that belongs to h and m is an index. 235.
235. Wait. Sounds like the example 3 to 3.
Here?
Yeah.
No, I don't know.
Okay.
Isn't written here?
It's like 1, 2, 2.
Oh, it could be here then. Okay. Is it
It's 6.
okay? Just yeah, it's 6. Yeah, I have to. That's it.
Right now? Or
Yeah, no, it's also 6. I think. Okay, I'll double check. Okay, yes,
it's
sorry. Okay. So that n belongs to h. Now, if I look at that, there exists m and z such that m belongs to h. Now, if m belongs to h, then minus m also belongs to h. Since h is a subgroup of z. Now, what can I say here? Now, if m and minus m belongs to h, I know that at least one of m, one of these two, is strictly positive. M or minus n is positive. Hence, the set S of m and n such that m belongs to h is basically h intersection n is not empty. Subset of n. Therefore, the non-empty subset of n. Therefore, there exists this set by dual ordering principle as a minimal element. Therefore, h intersection n as a minimal element. Let's call it m0. Okay. The claim is that h is equal to n zeros. Okay. That's clear. n0 plus h, then k times n0 belongs to h for all k and z. This is because h is subgroup. Hence, n0 z subset h. Now to prove the reverse, let h be h, and let q and r be z, such that h is equal to q and 0 is r, where r is between 0 and 0. Is it h? And q and 0 is h. Hence, h. Hence, r is an h. Now, r is a non-negative integer that is strictly less than n0. That belongs to h. Since r is strictly less than n0, and n0 is the minimal positive integer in h, then what? Then r must be 0. Otherwise, that would contradict the minimality of n0. So h is equal to q and 0, and hence will belong to n0 set. Therefore, h is contained in n0, and hence h is equal to n0 set. Okay. Now let's move on to other exercises. It's like every 15 minutes because the room is not test. That's 6. The room, you need room at 6. Right. No, or it's 235. It's not 235. Okay. Yeah. Okay, great. Now, let's do another example. Of cyclic groups, or of normal subgroups. Three. It should be a group and h. So remember that we said that h is normal. 6. Yes. You need room at 6, right? Okay. That's okay. No, we can write outside. You can wait, but I'm recording.
Sorry.
So let G be a group and H a subgroup of G.
Oh, where do you want to start? Sorry, can you repeat that? Can you repeat what you said?
I'm recording up to 35. You can stay. You can stay in. Don't worry. You can stay in. It's not a problem. So let G be a group and H. I'll finish at 6. Let H be a group and H a subgroup of G. Recall that H is a normal subgroup. If GH is equal to HG for all GG. Now prove that the following are equivalent. GH is equal to HG for all GG. And 2 X inverse belongs to H all X and G. Okay, so let's build these things. One implies two. You know, if the left coset is equal to the right coset, if GH is equal to HG, I need to show that XH X inverse belongs to H for all X and G and H. I mean, we start there. So let X be G and H is equal to and H. What is XH X inverse? I need to show that XH X inverse belongs to, we need to show XH X inverse belongs to. First of all, notice that XH belongs to XH because it's XH, right? Because it's X times an element of H. Now, by assumption, XH is equal to HX. So XH belongs to HX. Now, what does it mean that XH belongs to HX? It means that there exists H prime in H such that XH is prime with X. Let's do that. Let's multiply by X inverse. Hence, X H X inverse is equal to X prime. So 1 implies 2, and this is done. Now I need to show that 2 implies 1. Great. If I need to show that 2 implies 1, let G be G, and let X, well, not let X, let A belong to GH. We need to show that A belongs to HG. Now, if A belongs to GH, implies there exists H and H, such that A is equal to GH. Now, GH, the inverse, belongs to H by assumption, right? X, H, X inverse belongs to H for all X and G and H and H. So if I apply that assumption, how much time do you need? 5 minutes? I have 5 more minutes. Yeah. For all GH, G inverse belongs to H. And hence, GH, G inverse is equal to H prime, sum H prime and H. Well, what is this? This is A times G inverse is equal to H prime. So this is A is equal to HG H prime G. So A belongs to HG. Hence, GH is contained. Now we will show the reverse equality. So let B be in HG. We can write B as H tilde G for some H tilde H. Now the thing here is to apply that the assumption 2 in a nicer way. Notice that G inverse H tilde H belongs to H, right? Because I can write this as G inverse H tilde G inverse inverse. So if I have an element X in G times an element in H times an element in G, the inverse of the same element in G, and this one belongs to H. Hence, G inverse HG, still G, is equal to some, let's say, H2, or some H2H. So what? So let's write this. So G inverse H tilde G is equal to H2, and then H tilde G is equal to G H2. So G is equal to G H2. So B GH and hence G GH hence okay. Great, sorry, so they need the room in 5 minutes. Maybe I'll see if you guys have questions. Any questions, by the way? Any questions? I guess it's good, right? No questions? No questions? Are we good? Great. Okay. So yeah, okay, so I'll end this.